Hello, my name is Hans Burgerhof and I work as a statistician in the UMCG. This video is part of a series of videos about medical statistics. In this video I will give you some information about statistical tests for paired or matched observations. We will see examples in which the outcome variable is continuous, ordinal or binary. In previous videos we saw statistical tests for independent groups. In this video we will look at paired or matched observations. To make sure you're all aware of the difference between independent groups and paired observations, I will give you an example of each situation. A well-known example of a situation in which we compare independent groups is the randomized controlled trial. Respondents are randomized to, for example, two groups, a control group and an experimental group. We observe n1 values of the outcome variable in the control group and we have n2 observations in the experimental group. The observations are unrelated. An example of paired observations is the design in which respondents have been measured twice on the same variable. For example, blood pressures before and after a physical exercise on the same n individuals. The observations within an individual are related. In this video we will see examples of several paired tests. If we have a continuous outcome variable and the changes between the related observations are normally distributed, we can use the paired t-test. If the differences are not normally distributed, or the data are ordinal, we can use the sign test or Wilcoxon signs rank test. For binary pair data, we can use McNemar's test. We will start with an example of a simple study concerning systolic blood pressures. In 40 individuals, the blood pressures have been measured twice, before and after an intervention. Also, the differences between the first and second observations have been calculated. For example, the first individual had a systolic blood pressure of 140 mm mercury on the first measurement and 125 on the second. So the difference between the two measures equals 15. We expect that the intervention will have an effect on the systolic blood pressure. The null hypothesis states that there is no effect. μ1 equals μ2. Or, equivalently, the difference between the means is 0. This is also equivalent to the null hypothesis that the mean of the individual differences equals 0. We will test this null hypothesis against the two-sided alternative. If the individual differences have a normal distribution, we can perform a paired t-test. This paired t-test, in fact, is the one-sample t-test applied to the individual differences. First, we check the assumption of normality. Please note that this assumption concerns the changes between the observations, not the observations themselves. We will just check it visually, either by looking at the histogram or at the QQ or PP plot. From the graphs in this example, we can conclude that the differences are reasonably normally distributed. To perform a paired t-test in SPSS, choose in the menu Analyze, Compare Means and Paired Samples t-test. In the next window you have to combine the two related variables into a pair and check OK. In the SPSS output you will find two tables. The first one will contain descriptive information on both variables. We want to test the null hypothesis that the mean of the first measurement is equal to the mean of the second measurement. The second table gives the result of the statistical test. The tabulated mean is the difference between the two means of systolic blood pressure 1 and systolic blood pressure 2. The given t-value has been calculated by standardizing the mean, 8.766 divided by the standard deviation of the mean, the standard error, in this case 0.585. This leads to a t-value of almost 15. The number of degrees of freedom is equal to the number of individuals, 40, minus 1, so 39. The p-value is given as 0.000, so we know the p-value is smaller than 0.001, which is clearly smaller than our significance level 0.05. The null hypothesis will be rejected, and we can conclude that the mean systolic blood pressure on the second measurement is significantly lower than the mean on the first measurement. The paired samples t-test is equivalent to the one sample t-test on the individual differences between the first and second measurements, as we can see from these tables. The mean of the differences is exactly the same as the difference between the means. Also, the calculated t-value, the p-value and the number of degrees of freedom are the very same as in the paired t-test. If the differences between the paired observations are not normally distributed, or the sample is too small to check it, we cannot use the paired t-test. I will show you an alternative test, illustrated by an example from the book of Kirkwood and Sterne. We would like to answer the question whether a certain drug is more effective than a placebo for individuals with sleeping problems. 10 individuals are included in a crossover design. All 10 individuals receive both drug and placebo in random order in 2 different nights, and the numbers of hours of sleep are recorded. What to do if the individual differences between the numbers are not normally distributed? Here you see the data from the book. The null hypothesis states that there is no difference in hours of sleep using drug or placebo. If this is true, the differences between drug and placebo hours will be random, and the probability that drug-induced sleeping hours will be larger than sleeping hours after taking placebo will be 0.5 if we ignore ties. From the data we can see that there are 7 negative differences, indicating that the individual slept longer after drug than after placebo. What is the probability of finding 7 minus signs, or more, if the signs have a binomial distribution with n equals 10 and probability of success equals to 0.5? The sign test is not in the book of Kirkwood and Sterne, but the idea behind the test is quite simple. Conditional on the number of individuals with a difference unequal to 0, so ignoring the ties, we expect to see 50% pluses and 50% minuses. We will calculate the probability of finding the number of observed positive differences, or even more extreme, if the null hypothesis is true. Looking at the number of negative differences will give the very same p-value. Here you see the formula of the probabilities in a binomial distribution. For more information, see the video about probability theory. To perform a sign test in SPSS, choose in the menu Analyze, Non-parametric tests, Legacy dialogues, 2 related samples and check sign. Fill in the 2 related variables and check the OK button. In the output, SPSS shows 7 negative and 3 positive differences, like we found. The two-sided p-value was calculated as 0.344. This value has been calculated using the binomial distribution, with parameters n equals 10 and p equals 0.5. We can check this value by using the CDF, the cumulative distribution function, in SPSS. The probability of finding 7 negative values, or more, is equal to 1 minus the probability of finding 6 or less, which is 0.1719. This is the one-sided p-value. Doubling this value will give 0.3438, which is the same as the result of the sign test, rounded to 3 decimal places. The conclusion is, according to the sign test, there is no significant difference between hours of sleeping after drug or placebo. The sign test only takes the signs of the differences into account, not the magnitude. Wilcoxon signed rank test also considers the absolute values of the differences. Performing the test by hand will take 4 steps, which will be illustrated in a minute. First, calculate the differences between the paired observations. Second, rank the absolute differences, no matter the sign. Third, sum the ranks for each sign. And fourth, determine the p-value. Before showing the Wilcoxon signed rank test, first a simple example of giving ranks. If we have these 6 observations, the smallest observation will get rank number 1, the next number 2, 3, 4, 5, and the largest observation will get number 6. If there are any ties, these observations will get the same rank number, which is the mean of the original ranks. So in the second example, the observations with value 13 will both get rank number 4.5. If we apply Wilcoxon signed rank test to the sleeping data, we will find this table. The first 3 columns are exactly the same as in the sign test. But now we will rank the absolute differences, so regardless of the signs, which are given in the 4th column. 0.6 is the smallest absolute value, so this observation will get rank number 1. Then 0.9 will get rank number 2, and so on. In the last 2 columns, the ranks of the negative differences are separated from the positive differences, and the ranks in each column are summed up. If the null hypothesis of no difference between drug and placebo is true, we would expect that both sums are almost equal. There are tables to determine the p-value. Another possibility is to ask SPSS for it. In the menu of SPSS, choose Analyze, Non-Parametric Tests, Legacy Dialogues, 2 related samples. Fill in the 2 related variables and check OK. The default output will give an asymptotic p-value, an approximation to the exact p-value. If you prefer the exact p-value, you will have to check the exact button in the SPSS menu. Here we see the output given by SPSS after checking the exact button. The exact two-sided p-value is 0.23, which is larger than 0.05, so we will not reject the null hypothesis. Based on this small study, there is no reason to conclude that the drug has more effect than the placebo. To end this video, here's an example of paired binary data. 54 individuals with eczema on both arms used 2 ointments, A and B, randomized over left and right arms. After a week's period, the individuals had to indicate whether the ointments had a positive effect or not. The total information can be presented in a 2x2 table. 16 individuals considered both ointments to be successful. 5 individuals said that both ointments were not successful. These 21 individuals, so-called concordant pairs, give no information about a possible difference between A and B. The null hypothesis states that both ointments have the same effect. If this is true, preference for one of the two ointments is by chance only. So we expect half of the so-called discordant pairs to give preference to A and the other half to give preference to B. Conditional on the fact that there are 33 discordant pairs, what is the probability to find 23 or more individuals giving preference to ointment B? This is a one-sided p-value. If we test the null hypothesis against the two-sided alternative, we will have to double this p-value. There is also a chi-square approximation to calculate this by hand. This is known as McNemar's test, and the formula based on the discordant pairs is given here. If you want to perform McNemar's test in SPSS, you will have to construct the cross-tabulation first. Choose Analyze, Descriptive Statistics, Crosstabs. Drag one variable in the rows and the other in the columns, and choose Statistics and check McNemar. In the output, 3 p-values will be given. The one-sided p-value has been calculated using the binomial distribution, as we can check. The probability of finding 23 or more equals 1 minus the probability of finding 22 or less. This one-sided probability can be rounded to 0.0175 and will give a two-sided p-value of 0.035. If alpha equals 0.5, the p-value is smaller than that, so we can reject the null hypothesis. Ointment B has a significantly better effect than ointment A. This was the information about pair tests. Please make the exercises and check your answers. If all exercises were correctly answered, you can reward yourselves with a drink. Or, if you do not like statistics, take 2. See you in another video.